So let us see another concept from chapter 4, moving charges and magnetism chapter. So here the heading is circular current carrying loop as a magnetic dipole. So you know what is a magnetic dipole? Electric dipole we studied in chapter 1. So electric dipole means two equal and opposite charges separated by a short distance. Dipole moment P is equal to 2A into Q. Same like that, we have magnetic dipole. Magnetic dipole means a short magnet of north pole and south pole, that is known as a magnetic dipole, and the dipole moment you will get it as I into A. Dipole moment is I into A. Dipole moment small m is equal to I into A. So here what we are going to see is, we are going to see that we have a current carrying circular loop. This circular loop is carrying a current I of radius r. Okay, and we have a point P which is at a distance x. So we will just consider certain parameters, and we will find that the magnetic field due to this current carrying wire will be similar to the magnetic field due to a magnetic dipole. Hence we will see that current carrying loop is behaving like a magnetic loop. Okay, so coming to the diagram, we have a current carrying loop carrying current I, and we have a point P which is kept at a distance x. So finally we will see that this is behaving like a magnetic dipole. So I just showed a small magnet over there. Okay, so what we require is a current carrying loop of radius r carries a current I, and we have a point P along the axis which is at a distance x. Okay, and magnetic field at that point P, or magnetic field at the axis of a current carrying loop, we have the formula from Biot-Savart's law derivation. We have the formula mu 0 IR square divided by 2 r square plus x square raised to 3 by 2. And here we can see the distance x is very much greater than the radius r. So what you can do is, in the denominator that is r square you can neglect. Assuming x is very much greater than r, so you can neglect that r in the denominator. So if you neglect r in the denominator, mu 0 I r square divided by 2x square raised to 3 by 2. A square is to 3 by 2. If you solve, you will get it as x cube. Okay. So mu 0 I r square divided by 2x cube. Now in the next step what we will do is, we will multiply numerator and denominator by pi. Why we are doing like that is because over here we have r square. So if I apply pi r square is the area of a circle. Okay, so for that I'll multiply numerator and denominator with pi. So mu 0 I pi r square by 2 pi r cube. So I r square is area. So for I r square I can substitute it as area, 2 pi x cube. Okay, and as I told, I into A is magnetic moment. So magnetic moment is I into A. I into A is magnetic dipole moment. So I will substitute that. So this will become mu 0 by 2 pi m by x cube. Okay. Now what I'll do is I'll multiply 2 over here, and this will become 4 pi. So you will get magnetic field is equal to mu 0 by 4 pi 2 m by x cube. Okay. In first chapter we studied axial magnetic field of a electric dipole. Similar was the formula. Okay. Over here this is magnetic field due to a circular wire. We got a similar formula as that of a magnetic field due to a magnetic dipole. So mu 0 by 4 pi 2 m by x cube. So what we can conclude, hence a planar current carrying loop can be considered as equivalent to a magnetic dipole having a dipole moment m. Okay, so that is the derivation for showing that a current carrying wire behaves like a magnetic dipole. Thank you.